Good day and welcome back for the second installment on related rates. So recall from our previous discussion, when it comes to related rates problems, these are challenging word type problems that do require quite a bit of practice. But the nice feature is that we have a procedure or a mindset that we can use when we approach these problems. So just to very quickly give you that recap from our previous discussion, what we should do is read the problem carefully. And as we're reading the problem, we want to draw a picture that somehow represents the situation. Any quantity in the problem that is changing with respect to time, we should somehow assign a variable, so some type of letter or symbol. Once we have assigned these variables, what we want to do is see if we can come up with some equation relating them. And along the way, we should also indicate specifically what rate of changes do we know and what rate of change do we want to find. You will specifically have points awarded to you for writing that information down in the problem. Once you have that equation relating the variables, differentiate both sides implicitly with respect to t, and then solve for the desired rate of change. Once you have isolated that rate of change that you want, that's when we substitute in the specific information. It's going to be tempting to substitute that information in earlier, but we really have to fight the urge and remember that's the final step of the problem. So let's hopefully illustrate this idea in the below example. What we are told is that a perfectly spherical snowball melts so that its surface area decreases at a rate of 1 square centimeter per minute. What we would like to do is find the rate at which the radius decreases when that radius is 10 centimeters. So a very, very standard problem. We're starting off with this spherical snowball. So roughly speaking, something like this. And as I've told you many times, and I will continue to tell you, your pictures do not need to be perfect. Far from it. Hopefully they'll just kind of give you an idea of what's going on in the problem. So in this problem, we want to think, what do we know? What do we want to find? The information we are given. The surface area decreases at a rate of 1 square centimeter per minute. So I'm going to go ahead and introduce some notation. We'll say S represents the surface area of our perfectly spherical snowball. And what we know is that ds dt, the surface area, and the key word is decreases at a rate of 1 square centimeter per minute. So pause the video and write down what ds dt is equal to. And hopefully what you've written down is that it's minus 1 square centimeter per minute. And note the negative is due to the fact that it's a decreasing quantity. What we want to find is the rate of change of the radius when the radius is 10 centimeters. So we would like to find dr dt when r is equal to 10. And just to foreshadow a bit, when we do find this rate of change for dr dt, should it be positive or negative? And because the radius is decreasing, that dr dt should be negative when we find it in a few minutes. Now, in order to proceed with this problem, we need an equation relating the variables. So that is, what is a way to represent the surface area of a sphere with respect to the radius? And I'm going to kind of just do a few calculations to the side to maybe help us out here. If I was to instead ask you questions about a circle, I think you could probably give me much quicker answers. So if we happen to have a circle of radius r, I want you to write down for me what is the area, what is the circumference. the area of this circle is pi r squared, and its circumference is 2 pi r. And I want to note something that now, as sophisticated students of calculus, you can see and understand as well. To get from the area to the circumference, what did you do mathematically to that top equation? It kind of looks like you just differentiated it with respect to r. Now, in general, if we were to have something now, maybe say like a sphere, that same idea applies in terms of volume and surface area. So the more familiar relationship that we usually recall is that the volume of a sphere is 4/3 pi r cubed. What would you guess is the surface area with our above observation? Well, if you differentiate that with respect to r, the 3's cancel, and you have 4 pi r squared. And that represents the surface area of a sphere, and this just might be a way of helping you to kind of keep track of and remember those formulas. So the desired relationship that we have in this problem is that the surface area is 4 pi r squared. And I'll throw in here, I know a common question that students will ask me is, what types of formulas and equations do I have to remember? And it's really all about, when it comes time for the exam, what should you be able to recall and be familiar with? And for the exam, I'm not going to try to trick you or pull some random or obscure formula out that I expect you to remember, but instead, anything that you would see on an exam would be familiar to something that we've seen in class, so throughout these videos, in a graded homework problem, or a class worksheet. So for example, these relationships and formulas we have to the right are now things that I can assume we are familiar with. Since we have this relationship between the surface area and the radius, we are now in this ideal scenario to differentiate implicitly. And when we differentiate implicitly, on the left-hand side, we have ds dt, and on the right-hand side, working across, 4 pi is a constant. The derivative of r squared would be 2r, and it's implicit, so dr dt. And this is where we go back to what we want to find. I need to know what is dr dt. So I'm going to isolate dr dt in this equation, and when I solve for it, usually just for convenience or my preference, I'll put that dr dt in this case on the left-hand side. So we have ds dt now on the right, and we are going to divide everything by 8 pi r to isolate dr dt. And we're in an ideal scenario. We want to know what is dr dt when r is equal to 10 centimeters. So r becomes 10, and we know that ds dt is minus 1. And I'm going to simplify this just ever so slightly, and I'm going to write this as minus 1 over 80 pi. And I will throw out there that we should always include units. But at the same time, you don't need to overthink what the units are. Just go back to the variables we were dealing with. Here it's a rate of change of the radius with respect to time. So radius is measured in distance. Distance is in centimeters. Time is in minutes. So this rate of change, the units will be distance per time unit. And we now have that desired rate of change. And I invite you at this point to kind of pause the video and go back through the procedure that we have used in this problem and compare it to the procedure described above. This is a very standard problem, and this is the procedure that we will use to solve it. So we'll finish this video up with an additional example. But before diving in, I want to give you my standard reminder here. Related rates problems are challenging, and they do require you to practice them. These are very difficult problems to learn and master purely by listening or watching someone else do it. It really requires you to sit down and put in the work. So make sure that you're going through suggested problems. If you have questions, do not hesitate to reach out. So with that being said, let's jump into our example. So just reading through this, the angle of elevation of the sun is decreasing at a rate of 0.25 radians per hour. Okay, so we have a sun involved. How fast is the shadow cast by a 400-foot tall building increasing when the angle of elevation of the sun is pi over 6? So this is most definitely the type of problem that requires a picture. So we have a building, which we know is 400 feet tall. And remember, your pictures don't have to be perfect, far from it. So we have a building here, maybe with some windows and a door at the bottom. And we know that it is 400 feet tall. Furthermore, we know the sun's involved. So somewhere up here, we have our sun, and it is casting a shadow, which I can get in my picture. I'm going to draw it as a dashed line until right where it hits the building. So something along those lines. I will let this angle, which I will call theta, that would represent the angle of elevation of the sun. So theta is the angle of elevation. And we will let x, and you could choose whatever, symbol or letter you prefer, but in this case I'll let x be the length of the shadow. And I really think for this problem, once we get that picture drawn, it should hopefully make a little more sense. It's difficult to just see and hear the words, but the image really ties it all together. So the first thing we want to think about is, what do we know? What are we going to find? So in this problem, we are told the angle of elevation of the sun is decreasing at 0.25 radians. So that tells us that d theta dt is equal to minus 0.25 radians per hour. And do make sure that you're paying particular attention to words like decreasing or increasing. Because it's decreasing, we know it's going to be a negative rate of change. What we want to find is how fast is the shadow increasing when theta is pi over 6. So we want to find what is dx dt precisely when theta is equal to pi over 6. And this is a very typical position to be in. We've drawn a picture. We've introduced notation or variables for all of these quantities that are changing with respect to time. We've indicated precisely the rate of change that we know and the rate of change that we hope to find. The next step is, what is an equation relating our variables of interest, theta and x? And what I would like you to do is to pause the video, use the fact that we have some right triangle involved, and see if you can write down an equation relating theta and x. So hopefully you've written down an equation, and what I want to note is we have one angle and we know two legs of a right triangle. So the typical equation that we have most likely written down and that I would usually start with is that tangent of theta is equal to opposite over adjacent. So 400 over x. And this is a perfectly good approach. Now, we do need to differentiate implicitly with respect to t, so it would be more convenient to have the reciprocal here, that is x over 400, instead. And we could easily get that by rewriting this down in an equivalent form. And let me kind of emphasize, you don't have to, but it might be more convenient if we write cotangent of theta is x over 400. Once we have this relationship, and you could choose whichever one you prefer, we differentiate both sides implicitly with respect to t. And the reason I chose to go with x over 400 is that's a simpler or easier derivative for us to evaluate. We would just get 1 over 400 dx dt. And on the left-hand side, we differentiate implicitly. So we think the derivative of cotangent is minus cosecant squared. And because it's an implicit derivative, we multiply by d theta dt. So we've differentiated this equation relating theta and x. What we want to find is dx dt. So let's go ahead and isolate that. So to isolate the dx dt, we are going to multiply both sides by 400. And I'm going to switch sides just for convenience. Dx dt would be minus 400 times cosecant squared d theta dt. And what we want to know is dx dt at that angle of pi over 6. And we can just substitute that in now. So dx dt when theta is equal to pi over 6. This would be minus 400, and we have cosecant squared. So I'm going to write this as cosecant of pi over 6 quantity squared multiplied by d theta dt. And d theta dt is minus 0.25, which I'll write as minus 1/4, hopefully to help simplify in a moment. So the final thing that we need to do is evaluate this trig function cosecant at the common angle of pi over 6. And remember, we should always evaluate trig functions at common angles. So you need to be familiar with this. Cosecant of pi over 6 is 1 over sine of pi over 6. And just take a moment and write in there for me, what is sine of pi over 6? It's 1/2. 1 over 1/2 is 2. So cosecant of pi over 6 is 2. And note from a simplification perspective, 2 squared divided by 4 cancels. Okay. Also note from a simplification perspective, a negative and a negative cancels. And the only quantity left that has not canceled is a 400. But we always need to include units with these problems. We have found dx dt. So x is representing the length of the shadow, and we're measuring distance in our problem in terms of feet. So dx dt would have units that are in terms of distance per time unit. So feet per hour. So we should always include our units, but at the same time, you don't have to overthink the units. Use your intuition. So that completes the problem. As usual, I'm going to strongly encourage you to work through suggested problems. Reach out to me if you have questions. We will continue on with a more involved example in our next video. So stay tuned and take care.